In this video, we are going to learn how modular arithmetic and finite fields work. We will also learn why modular arithmetic is the preferred form of mathematics for cryptographic applications, particularly zero-knowledge proofs. This video will help you become familiar with how to do math using modular arithmetic. In modular arithmetic, our number system is limited to the integers 0 to some prime number minus 1. For example, if the prime number is 7, then only 0, 1, 2, 3, 4, 5, and 6 exist. If we add 1 to 6, the addition wraps around and becomes 0 instead of 7. If we multiply 3 by 3, we get 9, but this wraps around to become 2. To see how this wraparound works, imagine that we have a table with 7 columns. The first row are the numbers 0 through 6, the second row are the numbers 7 through 13, and the third row has the numbers 14 through 20, and so on. For each of the rows, the first column is a multiple of 7. The second column is a multiple of 7 with 1 added to it. The third column is a multiple of 7 with 2 added to it, and so forth. Since 9 is in the third column, that means it can be computed as a multiple of 7 plus 2. Therefore, we map 9 back to 2 and say that 3 times 3 results in 2. Initially, it might seem like this is a useless way of doing math. After all, we have a lot fewer numbers to work with. But despite having a much smaller number system, modular arithmetic can still do most of the traditional arithmetic and algebra we are used to. It just works a little differently. We can add, subtract, multiply, divide, raise a number to a power, compute square roots, find roots of polynomials, solve systems of equations, and so forth. As we will learn in this video, all the math will be surprisingly consistent with how we do math normally. The crucial advantage of modular arithmetic is that there is no precision loss. Let's look at the following common problem in programming to motivate why we might want an alternate number system. Any programmer knows that 1/3 plus 1/3 plus 1/3 is not equal to 1 because 1/3 cannot be represented in binary. In the real world, we can just check that 0.999999 is really close to 1, so we'll just round it. But in the context of cryptography and zero-knowledge proofs, we can't say, "Trust me, bro, I rounded the number correctly." In a zero-trust environment, there cannot be any ambiguity about what numbers we are dealing with, and it's really inconvenient not to have a number like 1/3. So how can we carry out the computation of 1/3 plus 1/3 plus 1/3 without any precision loss? It turns out the solution is to perform the arithmetic modulo a particular prime number. For example, if we choose our prime number to be 7, then that means we do our normal arithmetic, divide the answer by 7, and return the remainder as the answer. For example, if we do 4 times 5 equals 20, we divide 20 by 7 and get 2 remainder 6, so we return 6. In modular arithmetic, we say that 4 times 5 equals 6 modulo 7. Before I move on, I would like you to know that for most of the mathematical examples we will encounter from here onward, I have chosen 7 as the prime number for computing the modulo. When we divide by 7, the remainder must be one of the values 0, 1, 2, 3, 4, 5, or 6. Thus, the values in our number system are only 0, 1, 2, 3, 4, 5, or 6. There aren't any fractions. So where does the number 1/3 come from? One way to think about 1/3 is that it is the solution to a plus a is equal to 1. But in our case, we are solving the equation a plus a is equal to 1 modulo 7. It turns out that 5 is the solution to the equation because 5 plus 5 is equal to 15, and when we divide by 7, we get a remainder of 1 with no precision loss. Therefore, 5 corresponds to 1/3. But how did I know to map 1/3 to 5 in this example, and how would I do that in general? Let's explain modular arithmetic from first principles, then work our way towards figuring out how we can solve the problem we just showed. Modular arithmetic means that after we do any addition, multiplication, subtraction, or division, we take the result and compute the modulus with some prime number. The modulus is a fancy word for remainder after division. So 10 modulo 7 is 3, 11 modulo 11 is 0, 15 modulo 3 is 0, 8 modulo 7 is 1, and 15 modulo 7 is 1. We call a finite field the set of numbers that exist in this number system. For example, if we do everything modulo 7, then only the numbers 0, 1, 2, 3, 4, 5, 6 exist. A number like 8 simply turns into the number 1, 9 turns into 2, 10 turns into 3, 11 turns into 4, and so on. Eventually, we will complete all the numbers and 14 will turn into 0, 15 into 1, and so on. To convert a normal number into a member of the field, we compute the modulus of that integer with the prime number. This means that 8 maps to 1, 10 maps to 3, and 49 maps to 0. If we draw a table like this, it kind of becomes more obvious how the integers get mapped. If we say that 8 maps to 1, the technical word for that is that 8 is congruent to 1. We wouldn't exactly say that 8 equals 1 because that would trigger mathematicians. So to avoid getting cancelled by mathematicians, we are going to use their smart-sounding vocabulary and say that 8 is congruent to 1 modulo 7, 9 is congruent to 2 modulo 7, 10 is congruent to 3 modulo 7, and so forth. Here, the triple equals means congruent. Obviously, 8 is congruent to 1 is only true because we are doing everything modulo 7. If we had chosen some other prime number to do the modulo with, then 8 would be congruent to something else. For example, if the prime number is 5, then 8 would be congruent to 3.
When we draw the table like this, we see that numbers in the same column are congruent to each other.
Here is the first rule of modular arithmetic. If A and B add up to C, then the number congruent to A added to the number congruent to B equals the number congruent to C. Let's see some examples. 22 plus 18 is equal to 40. We also have that 22 is congruent to 1 modulo 7, 18 is congruent to 4 modulo 7, and 40 is congruent to 5 modulo 7. And it is obvious that 1 plus 4 is equal to 5. By the way, you can compute the modulo in your head by finding the closest multiple of 7 for the number. 21 is a multiple of 7, so 22 minus 21 is 1. 14 is the closest multiple of 7 for 18, and 18 minus 14 is equal to 4. And 35 is the closest multiple of 7 for 40, and 40 minus 35 is 5. Let's move on to a more interesting example. How about 33 plus 20? The sum is 53. 33 here is congruent to 5. 20 is congruent to 6. And 53 is congruent to 4. And indeed, 5 plus 6 is equal to 11, but we have to do mod 7, which gives us 4. The reason why integers which sum together also have their congruences sum together is pretty simple. If we divide both sides of a balanced equation by the same number and take the remainder, we'll get the same remainder on both sides. What we showed about addition earlier is also true of multiplication. With regular integers, 10 times 5 is 50, 10 is congruent to 3, 5 is congruent to 5, and 3 times 5 equals 15, which is congruent to 1. 50 is also congruent to 1, as the next closest multiple of 7 is 49. I know you are still wondering how I turned 1/3 into 5 from the earlier example, but before I show you that, I'm going to show you another cool property of finite fields. The rule we just showed also works with negative numbers. Let's take our table from earlier and extend it in the other direction. It should be no surprise that the negative multiples of 7 are congruent to 0. After all, the positive ones are also. But what is the interpretation of -2 being congruent to 5? In order to show you this, let's learn how to compute the modulus when negative numbers are involved. The modulo of a negative number, modulo a positive number p, is always a positive number in the range 0 to p minus 1. To determine the result of a negative number, modulo a positive number, we just add enough multiples of p to the negative number such that the final result is 0 or more, and the amount we exceed 0 by is the remainder. For example, if we want to compute -10 modulo 7, the smallest positive multiple of 7 that we can add to -10 to make the sum positive is 14. -10 plus 14 equals 4, so the remainder is 4. Therefore, -10 modulo 7 is 4. If we want to compute -4 modulo 7, the smallest positive multiple of 7 we can add to -4 to make the sum positive is 7. -4 plus 7 is 3, so -4 modulo 7 is 3. If we want to compute -7 modulo 7, we get 0 for the same reasons. 7 is the smallest positive multiple of 7 that we can add to -7 to make the result 0 or greater. I've just given you the graphical and intuitive explanation for how to think of a modulo with a negative number. Let's adopt Python to see how it works out mathematically. If we check in Python what -2 modulo 7 is, we get 5. Why is that the case? Remember, the modulo is the remainder after division. If we divide -2 by 7, we get -0.2857. However, when we compute remainders, we don't do float division, but rather we do integer division. In Python, integer division is the double slash. The code just shown is saying that -2 divided by 7 using integer division is -1. Why is it -1 instead of 0? When we do integer division, we round down. For example, if we divide +2 by 7, we get 0, because 2 divided by 7 equals 0.285, and when we round down, we get 0. However, if the result is negative, rounding down means we round towards negative infinity, not 0.
Thus, -2 divided by 7 rounds down to -1 because -0.2875 rounds down to -1.
Now that we know that -2, integer divided by 7, is -1, how do we compute the remainder? The relationship between dividend, divisor, and quotient is as follows. Dividend is equal to quotient times divisor plus remainder. We encourage you to pause the video and try out a few examples to convince yourself that this is indeed the case. 15 divided by 7 is 2 with a remainder of 1. 12 divided by 2 is 5 with a remainder of 2. And 11 divided by 2 is 4 with a remainder of 3. Let's revisit why -2 modulo 7 equals 5. We know that -2 integer divided by 7 is -1, so we'll plug those values into the formula. We will plug -2 into the dividend, we'll plug 7 into the quotient, and we'll plug -1 into the divisor. And we'll solve for the remainder, and we get 5. This matches what Python says. Let's look at another example. What is -4 modulo 7? -4 integer divided by 7 is -1 because -4 divided by 7 is -0.5725, and when we round down, we get -1. Therefore, -4 integer divided by 7 is -1. Now let's use our formula from earlier and plug the values in to compute the remainder. Dividend is equal to quotient times divisor plus remainder, which gives us -4 is equal to -1 times 7 plus remainder. After we solve it, we get that the remainder is 3, and indeed, we see that -4 modulo 7 is 3. Let's look at one more example of taking the modulo of a negative number. What is -24 modulo 7? First, we compute -24 divided by 7, and we get -3.4285. We round that down and we get -4. Now that we know the dividend, divisor, and quotient, we compute the remainder. -24 is equal to 7 times -4 plus remainder, and we get 4 as the answer, which matches what Python gives us. To enforce this concept, we recommend that you pause the video for a second and compute -33 modulo 7 by hand. Then compare your answer to what Python gives you. Before we move on, it is worth pointing out that Python handles division with negative numbers in a different way to some programming languages. Rust rounds integer division to 0 for negative numbers. For example, -6 divided by 7 equals 0 in Rust, and -6 modulo 7 in Rust is -6. I will show you some Rust code in a few seconds. So if you do not have Rust installed on your computer, I advise you to open your web browser and use the website play.rust-lang.org. Here, Rust returns 0 as the answer, but if we go back to our Python terminal to check, we see that Python returns -1. This means that the modulo will not be computed in the same way. Similarly, -10 divided by 7 equals 1 with a remainder of -3. This interpretation of negative integers is also consistent with the relationship of the numerator is equal to quotient times denominator plus remainder. For example, if we plug in -10 for the numerator, -1 for the quotient, 7 for the denominator, and -3 for the remainder, the equation is still balanced. But mathematically, the correct answer according to number theory is what Python gives us. A negative number modulo a positive number should always be in the range 0 to p minus 1. However, you can get the correct answer from Rust just by adding p to the answer. For example, -2 modulo 7 is 5, but Rust returns -2. If we add 7, which is our prime number, to the -2 we got back, the final result will be 5, which is the correct answer. Similarly, -10 modulo 7 returns 4 in Python, but in Rust it returns -3. However, again, if we add 7 to -3, we get the same answer of 4. Note that adding p to the number we take the modulo with doesn't change the answer if the original answer was positive. For example, 4 modulo 7 is 4, but 4 plus 7 modulo 7 is also 4. Similarly, 10 modulo 7 is 3, and 10 plus 7 modulo 7 is still 3. This is because of the general rule that if a mod p is equal to b, then a plus p mod p is equal to b. So if we want our Rust code to return the correct answer according to number theory, we can always just add p to the answer and compute the modulo again. If the original answer was positive, the final solution will not change. A very important property of negative numbers is that a number added to its negative results in 0. Although there aren't any negative numbers in the set 0, 1, 2, 3, 4, 5, 6, if a number is congruent to a negative number, it can behave like that negative number. For example, 6 is congruent to -1. We expect that -1 plus 1 is equal to 0. Therefore, 6 plus 1 should be equal to 0 modulo 7, and that is indeed the case. Therefore, it isn't a problem that we don't have -1 in our set of numbers because 6 can serve that purpose. Similarly, 3 behaves like -4 in a finite field modulo 7, and 4 behaves like -3 in a finite field modulo 7. This is because 3 plus 4 is equal to 0 mod 7, which is congruent to -4 plus 4 is equal to 0. We could also think of 3 plus 4 equals 0 mod 7 as congruent to 3 plus -3 is equal to 0. Both interpretations are correct. Suppose we want to compute the negative of a certain number in the finite field. To do so, we simply compute p minus x, where x is that number. Since p is 7 in our example, we can compute that -1 is 6, since 7 minus 1 is 6. We see that -2 is 5, since 7 minus 2 is 5, and -3 is 4, since 7 minus 3 is 4, and so on. What about 2 plus 5 is equal to 0 mod 7? 2 is congruent to -5, and -5 plus -5 is equal to 0. Equivalently, 5 is congruent to -2, and 2 plus -2 is equal to 0. It doesn't matter if we interpret 2 as -5 or 5 as -2. The math will work out both ways. This is true for numbers outside of the finite field also, because their congruent equivalences will still add up to 0. Let's try a few examples. -13 is congruent to 1, and +13 is congruent to 6. If we add 1 plus 6 modulo 7, we get 0. What about -11 plus 11? That's 3 plus 4, which also adds up to 0 modulo 7. The terminology we use for this is additive inverse. The additive inverse is the negative of another number. -5 is the additive inverse of 5, and vice versa. And 5 is the additive inverse of 2 in our finite field. In a sense, 2 behaves like -5, and 5 behaves like -2. Why do we have a special term for pairs of numbers adding up to 0? Well, 0 is a bit special in the context of addition, because 0 is its own additive inverse. 0 plus 0 is 0, and any number added to 0 results in that number. Because the number 0 is special for addition, we have a special name for it, the additive identity. The relationship between additive inverse and additive identity is that a number added to its inverse is the additive identity. It is worth pointing out that computing 4 minus 6 modulo 7 is the same as computing 4 plus the additive inverse of 6. And just as adding positive numbers is consistent with adding their congruences, adding negative numbers together is also consistent with their congruences. Let's use -4 is congruent to 3, plus -6 is congruent to 1, is equal to -10 is congruent to 4 as an example. And 3 plus 1 is equal to 4, which is expected, since -4 plus -6 is equal to -10. Perhaps you are still wondering why we mapped 1/3 to 5. Let's look at it from this angle. Let us represent 1/3 by a. Doing this means we have a plus a is equal to 1, which implies that a is equal to 1/3, but in our set of numbers, 1/3 does not exist. We only have the numbers from 0 to p minus 1, and for modulo 7, that makes it p minus 1, which is equal to 6. In the finite field modulo 7, only the numbers 0, 1, 2, 3, 4, 5, and 6 exist. 1/3 is not one of the numbers. This gives us a situation where we are trying to find a plus a plus a is equal to 1 modulo 7. To arrive at the solution, we can try to brute force a by changing it to an element in our set of numbers starting from 0. First, we substitute a for 0. We have 0 plus 0 plus 0, which is equal to 0 mod 7, which equals 0. This is clearly not going to work, so we continue by plugging in the next element, which is 1, and we get 1 plus 1 plus 1, which is equal to 3 mod 7, which is 3, and that still doesn't work. So we move on to the next, which is 2. This gives us 2 plus 2 plus 2, which is equal to 6 modulo 7, which is still 6, which still doesn't work. We move on to 3, and we have 3 plus 3 plus 3, which is equal to 9 mod 7, which results in 2 and still doesn't work. Then we move on to 4, which is 4 plus 4 plus 4, which gives us 12 modulo 7, which is equal to 5, and that still doesn't work. Finally, this brings us to 5. And if we substitute 5, we have 5 plus 5 plus 5. This is equal to 15, mod 7 equals 1. And here we go. This is exactly what we want because 15 divided by 7 is 2 remainder 1. Therefore, we say that the solution of a plus a equal to 1 has to be 5. Therefore, 5 is 1/3 when we do arithmetic modulo 7. 1/3 maps to 5 because 5 behaves like 1/3. If you add 5 to itself 3 times modulo 7, you get 1. Similar to the additive identity, there is also a multiplicative identity. It is the number 1. That's because any number multiplied by 1 is the original number, and 1 multiplied by 1 is also 1. This is similar to how if we add 0 to any number, we get the original number. From this context, we can infer what a multiplicative inverse is. An additive inverse of x is another number x prime such that x plus x prime produces the identity element. The multiplicative inverse of x is another number x prime prime such that x times x prime prime is equal to 1. In regular numbers, the multiplicative inverse of a number is its reciprocal. For example, the multiplicative inverse of 5 is 1 over 5. The multiplicative inverse of -7 is -1 over 7, and the multiplicative inverse of 1 over 15 is 15. You will have to take this on faith for a second, but every number in a finite field besides 0 has a multiplicative inverse. For our running example of the set 1, 2, 3, 4, 5, 6, we can find the multiplicative inverse by brute force. We already found the multiplicative inverse of 3. We know that it is 5 since we established that 5 behaves like, or in other words, is congruent to 1/3. Now what is the multiplicative inverse of 1? Well, it's obviously 1 because 1 multiplied by 1 is 1. How about 2? Well, we know it isn't 1, 2, or 3 since none of those multiply to equal 1 modulo 7. If we multiply 2 by 4 modulo 7, however, we get 8, which is congruent to 1. Therefore, 4 is the multiplicative inverse of 2, and 4 is congruent to 1/2. We'll skip 3 and move on to 4. We saw earlier that 4 is the multiplicative inverse of 2, so immediately we know that 2 is the multiplicative inverse of 4. In other words, 2 is congruent to 1/4. Moving on to 5, we already know that 5 is the multiplicative inverse of 3. Therefore, 3 must be the multiplicative inverse of 5. In other words, 3 is congruent to 1/5 since 5 times 3 is 1 modulo 7. 6 is a little trickier, but if we try multiplying it by each member of the finite field modulo 7, we discover that 6 is its own multiplicative inverse since 6 times 6 is equal to 36, and 36 is congruent to 1 modulo 7. In regular numbers, -1 is its own multiplicative inverse, and we can see on the table that 6 is congruent to -1, so this makes sense. Here is what we observe computing the multiplicative inverse for every element in the finite field modulo 7. Every number except 0 has a multiplicative inverse. Each multiplicative inverse is unique. It never appears twice. If A is the multiplicative inverse of B, then B is the multiplicative inverse of A. Okay, cool. We know this is true for the finite field modulo 7, but would it be true for other finite fields like modulo 17 or modulo 31? Would it be true in general? As a matter of fact, these observations are true in general. But how do we know that these observations are true in general? I'm expecting my target audience is programmers, not mathematicians, so my proof is as follows.
Trust me, bro.
But on a serious note, if you really want to know why this is the case, you can look up a proof online. But here's the statement we want to establish. In a finite field, every number other than 0 has a unique multiplicative inverse. That is, a number that, when multiplied by the original number, results in a product of 1. Now that we have that out of the way, how do we compute the multiplicative inverse? Again, if I was speaking to math students, I would probably say something about Fermat's little theorem at this point, but I'm just going to skip that and jump straight to the code. Open your Python terminal and be sure you are running Python version 3.8 or higher. Set the prime number you're using the modulus for. We'll do p equals 7 for our example. Now pick the number for which you are trying to compute the multiplicative inverse. Let's pick x is equal to 4, then do power x, comma, -1, comma, p. We'll get 2 back. We can verify that 2 times 4 modulo 7 is equal to 1. In Python, pow of ABC is equal to a raised to the b power modulo c. To see that this works for arbitrary non-zero numbers and arbitrary primes, at least ones that fit on your computer, do power of x, -1, p times x modulo p, which equals 1. And try out a lot of different values for x and p, subject to the restriction that x is not 0 or a multiple of p, and p is prime. Why can't x be 0 or a multiple of p? Well, there is no multiplicative inverse of 14 modulo 7 because 14 is congruent to 0. Remember, the definition of the multiplicative inverse of x is x prime prime such that x times x prime prime is equal to 1. However, there is no x prime prime that multiplies with 0 to produce 1. But aside from that limitation, we can do any arithmetic we want to. If we want to compute 2/3, we can decompose it as 2 times 1 over 3, or 2 times multiplicative inverse of 3. Let's check this in Python. So 3 is congruent to 2 over 3. How can we test this? Well, if we add 1 over 3 to 2 over 3, that should give us 1. Let's test this in Python. We will assign 7 to p and assign power of 3 -1p to 1/3, then assign 2 times power of -3 1p modulo 7 to 2/3, and then we will perform the operation 1/3 plus 2/3 modulo p. And then we get 1. It works as expected. Now let's do something funky. How about 1 over 4 plus 1 over 3? The answer ought to be 7 over 12. Let's check this out in Python. We will assign 7 to p, then assign 4 -1p to 1/4, and assign power of 3 -1p to 1/3, and then we will do 7 times power 12 -1p modulus p, and assign it to 7 over 12. And then we'll do the assertion 1/4 plus 1/3 modulus p is equal to 7 over 12, and the assert statement does not trigger an exception because the equation is balanced. Let's look at a few more examples. Here is our table showing mod 7 from earlier. Note that 6 is congruent to -1. Since we know that -1 times -1 is equal to 1, what do we expect 6 times 6 mod 7 to be? We can immediately infer that we expect the result to be 1 because -1 times -1 is 1. Of course, we could actually compute 6 times 6 to be 36, and see that that is also congruent to 1. What about -5 times -5? We expect the result to be positive 25, which is congruent to 4. Looking at the table, we see that -5 is congruent to 2. And indeed, 2 times 2 equals 4, just as -5 times -5 is equal to 25. How about negative 1/2 times 2? We expect the result to be negative 1. Negative 1/2 is the additive inverse of 1/2. 1/2 can be computed in Python as pow2 -1 which gives us 4. But we want the additive inverse. The additive inverse of 4 is 3 since 4 plus 3 is congruent to 0. This could also be computed as 7 minus 4 is equal to 3. Therefore, negative 1/2 is congruent to 3. If we multiply 2 by 3, we get 6, which is congruent to negative 1. This is just what we expect to get when we multiply negative 1/2 by 2. By the way, you can compute the congruent equivalent of negative 1/2 as pow -2 -1 in Python and get 3. Python is smart enough to figure out what you are trying to do. What about negative 1/2 times negative 1/2? We saw from the previous example that negative 1/2 is congruent to 3. We know that we expect the answer to negative 1/2 times negative 1/2 to be positive 1/4. Well, if we use Python to compute the multiplicative inverse of 4, we get 2. And indeed, it is the case that 3 times 3 is equal to 2 modulo 7. Let's do one more example to drive the point home. What about 1/3 minus 1/2 is equal to negative 1/6? We can compute this as 2/6 minus 3/6 is equal to negative 1/6. Let's use Python to compute the congruent equivalences. P is equal to 7, 1/3 is equal to pow3 -1p, 1/2 is equal to pow2 -1p, and negative 1/6 is equal to negative 1 times pow6 -1p mod p. Then we can check that 1/3 minus 1/2 modulo p is equal to negative 1/6, which is true. The cool thing is, if we did that computation with regular numbers, we would have had precision loss, but not with modular arithmetic. Square roots are another aspect that behaves surprisingly consistent with regular numbers. Instead of doing our arithmetic modulo 7, let's increase it to 17. There are 3 square numbers here, 4, 9, and 16. Unsurprisingly, 2, 3, and 4 squared equals those numbers. But remember, square roots also have a negative solution. Negative 2, negative 3, and negative 4 are square roots of 4, 9, and 16. If we compute the congruences for negative 2, negative 3, and negative 4 modulo 17 in Python, we get 15, 14, and 13 respectively. Let's go back to the Python terminal to check this. This should also be clear if we draw the table from earlier. Now, if we square each of those numbers modulo 17, then we see that they are valid solutions for square root of 4, square root of 9, and square root of 16. But it gets even more interesting. It turns out that 2 has a square root in the finite field modulo 17. That doesn't mean that the square root of 2 is equal to 1.414 is congruent to 11. Rather, the interpretation is that 11 times 11 is equal to 121, and 121 modulo 17 is congruent to 2. So saying 2 has a square root in our finite field is more like saying 121 is congruent to 2, and 11 is the square root of 121. So how do you compute the square root of a number in a finite field in the general case? The algorithm is called Tonelli-Shanks, but you can just import a Python library to do it for you. The Python library is called libnum, and you can install it on your computer using pip, which is the Python package manager for Python packages or libraries. We will install libnum package first before we can use it in our next operation. Let's show how to compute the square root of 2 modulo 17. These are the functions we need to import. Given a finite field modulo p, not every number in the finite field has a square root. Therefore, we use the function hasSquareRoot mod prime power to check if the square root exists. For example, we can check if 2 has a square root modulo 17 with the following code. P equals 17, hasSquareRoot mod prime power 2p1, and it returns true. And indeed, 2 does have a square root modulo 17, as we discussed earlier. Let's explain the function arguments really quickly. 2 is the number we are trying to compute the square root for, p is the modulo of the finite field, and 1 is the power we raise p to. Why we might be interested in the power of a prime number is the subject for another day. For our purposes, we always set the third argument to 1. But 11 does not have a square root modulo 17. To compute the square root, we can do the following. We can quickly verify that both of these numbers are square roots of 2 modulo 17 by squaring them modulo 17. As another example, we can compute the square root of 4 modulo 17 as follows. And we can check that both of these are valid solutions to the square root of 4 modulo 17. If we plot a square root in normal arithmetic, we get something like this. To be technically correct, we also need to plot the negative solution. So we also need to plot the negative y values. The way we create plots is we loop over the x values and compute the y values. In modular arithmetic, this is no different. In a finite field modulo 17, there are 17 values we loop over. On the left-hand side, we have the code for generating the graph of y is equal to the square root of x modulo 17, and on the right-hand side, we have the graph. And you can see in the code that we have introduced another library for plotting graphs in Python. This library is called matplotlib, and you can install it using the same process we use for the installation of the libnum library. Let's look at what this is doing. First, we loop through every value of x. If the value of x has a modular square root, then we compute it. 0 only has one square root, which is 0, so we'll plot that. And if we check the graph at the point of origin, we see the plot for x is equal to 0. Moving the loop forward to x is equal to 1, we see that x has two square roots modulo 17. 1 and 16. It should be obvious why 1 is the square root of 1, but negative 1 is also a square root of 1. But negative 1 is not part of the finite field. Therefore, we need to find the number in our finite field that is congruent to negative 1, which is 16, as we will show now. The solution for 1 is intuitive, as the square root of 1 is 1. However, for 16, if we bring back the table for modulo 17 from earlier, we see that 16 is congruent to negative 1, and negative 1 times negative 1 is 1. Basically, 16 times 16 is equal to 256, which is congruent to 1 modulo 7. So now moving to x is equal to 2, we have a square root of 11, as we discussed earlier, because 121 is congruent to 2, and the square root of 121 is 11. 6 is the additive inverse of 11 because 11 plus 6 is equal to 17, which is congruent to 0. Since 11 is a square root, negative 11 is also a square root. 6 is congruent to negative 11, so 6 is also a square root. In general, if a number y is a square root of a number x, then negative y, or the additive inverse of y, will also be a square root of x. Therefore, we plot both 6 and 11. Moving to x is equal to 3, 3 does not have a square root modulo 17. That means there is no solution for x raised to the power 2 is equal to 3 modulo 17, so we skip that. Moving to x is equal to 4, 4 has the square root of 2 and the additive inverse of 2, which is 15. We keep looping, and for every x value that has a modular square root, we plot the square roots. And lastly, when x is equal to 17, 17 modulo 17 is equal to 0. This is what the square root looks like in modulo 17. Let's compare this plot to the original plot of y is equal to the square root of x. For real numbers at x is equal to 0, we have only one solution, a single point. But for every other value, the y solutions are horizontally symmetric. In both cases, this is the same as what we saw in our original plot of y is equal to the square root of x over real numbers. There is a single solution at x is equal to 0, but for every other x value, we have two horizontally symmetric y values. Hopefully you are getting the idea that if we take regular math and change everything to be done modulo a prime number, it just works. Let's look at some more examples to enforce the point. Suppose I ask you to solve the following system of equations. Equation 1 is 3x plus 2y equals 7.5, while equation 2 is 4x minus 3y is equal to negative 7. After solving the equation, we see that x is equal to 1 over 2 and y is equal to 3. But is this true also in modular arithmetic? To check this, we convert all the numbers in question to their congruent equivalences. 3 becomes 3 modulo 7, 2 becomes 2 modulo 7, 7.5 becomes 15 divided by 2, which is congruent to 4 modulo 7, 4 becomes 4 modulo 7, negative 3 is congruent to 4 modulo 7 also, and negative 7 is congruent to 0 modulo 7. Next, we convert our solution of x is equal to 1 over 2 to 4, and y is equal to 3 to 3. 3 times 4 plus 2 times 3 modulus p, which is 7, is equal to 4. And our assertion is right because 7.5 is congruent to 4 modulo 7. Likewise, 4 times 4 minus 3 times 3 modulo 7 is equal to 0, which is right because negative 7 is congruent to 0 mod 7. Now let's take it a step further. What if I ask you to find the roots of the polynomial x raised to the power 2 minus 7.5x plus 11? You would probably plug it into this formula which has different names. Some know it as Bhaskarat's formula, others call it the almighty formula because why not? But we'll refer to it as the quadratic formula as it is generally known. And you will see that the roots are 2 and 5.5. If our finite field is p equals 19, that corresponds to 2 and 15. Now I will show you how 5.5 is congruent to 15 using Python. I assign 19 to p and use the assert statement. I assert that 15 is equal to 11 times power of 2 negative 1 19 modulus p, and we see that 11 divided by 2 is equal to 5.5. Therefore, we know that the root of x raised to the power 2 minus 7.5 plus 11 are 2 and 5.5 with regular numbers, and 2 and 15 in the finite field modulo 19. But we could also convert the coefficients of the polynomial into their congruent equivalences, put them into the quadratic formula, and derive the same answer. However, our quadratic formula needs to be transformed to carry out the operation using modular arithmetic instead of regular arithmetic. Here's the regular formula. We don't have division in modular arithmetic. Instead, we multiply by the multiplicative inverse of the denominator. We also need to compute the square root using a modular square root, not the default square root of Python. Then we plug the modular congruences for a, b, and c into the modified quadratic formula. Recall that the original polynomial is x raised to the power 2 minus 7.5x plus 11. The congruent equivalences of the polynomial coefficients are 1, 2, and 11. 1 is congruent to 1 modulo 19, negative 7.5 is congruent to 2 modulo 19. We can compute negative 7.5 as negative 15 times the multiplicative inverse of 2. Let's go back to Python now to verify this. And 11 is congruent to 11 modulo 19. In the code I'm about to show you in Python, we plug a is equal to 1, b is equal to 2, and c is equal to 11 into the modified quadratic formula. The division step is computed by modular inverse, and the modular square root is computed using the same library from last time. Here is how to do that in Python. And indeed, we see that we have arrived at the same answer for roots of 2 and 15. Here is the plot of the original polynomial x raised to the power 2 minus 7.5x plus 11, but in modular form. Note that the roots are at 2 and 15 like we predicted. So to wrap everything up, if we pick a finite field with a particular prime number, we can convert any arithmetic to the congruent equivalent in the finite field and carry out the same computation with no precision loss. Whenever we add, subtract, or multiply numbers, we return the modulo of the result. Division is simply multiplying the numerator by the multiplicative inverse of the denominator. Any number in a finite field that is a square number or congruent to a square number has a square root. Basically, any math you do with fractions, square roots, or polynomials just works in a finite field. If you want to see more code examples and useful libraries for modular arithmetic, check out our article on finite fields at www.rareskills.io/post/finite-fields. The link is in the description. This video was based on that blog article. Thank you for watching.